Okay, so now we're going to start putting this into action, this idea of finding volumes of solids. In this particular section, what we're going to do is we're going to focus on what we call uh, solids of revolution. So these are essentially three-dimensional solids that are generated by taking a two-dimensional region, something like area under a curve, or in between two curves, and rotating it about an axis, be it vertical or horizontal, resulting in some sort of a three-dimensional shape whose cross sections are circular disks. And that's why this is going to lead us to what we refer to as the disk method. So let's start with a kind of a nice, easy beginning problem. So let's begin with the region bound by the curve f of x equals x squared, the x-axis, and then the interval between 0 and 3. So what would this look like? Well, if we were to draw this, we would have our, we're essentially just looking here in the first quadrant. So here's y, and this is not really going to be to scale, but hopefully that's okay. And we'll have our curve x squared, and this is going to go to x equals 3, so from 0 to 3. So when we look at this bound area, if we kind of came up and bounded in, this is the area in question that we'll be kind of working with throughout this problem. So this little trapped region right here. All right, so now that we sort of visualized that area, what we're going to do is we are going to take this region and rotate it about in this case, the x-axis. Now, the axis that we rotate areas around are going to change from problem to problem, so we want to make sure we pay close attention to that. But in this case, we're gonna just rotate this around the x-axis. Oftentimes, what we do when we're dealing with solids of rotation is we start with this two-dimensional area, and then we draw a little arrow around the axis that we're going to rotate about. All right, so let's, again, we're going to have to kind of test our drawing abilities here, and it's not going to be perfect, but hopefully it'll make sense. If we did rotate this, then here's the scenario that we may be looking at now. So again, this is the y-axis. Here's our axis of rotation, the x-axis sort of coming out at us. We'll call that x, and this is y. And our boundary curve, so here's that parabola kind of coming along the x-axis there. And this, supposedly would stop here at 3. And now what we do is we consider what this would look like if we were to rotate it. And essentially we're going to get sort of like a horn-shaped solid. So each of these, this is that 3D solid that we've generated here. All right. Now, as we think about what's going on here, this kind of 3D solid that we've got, much like what we did in the previous example, where we were asking ourselves, well, how do we now find the volume of this? We concluded that we needed two particular things. We needed the bounds that this volume was rotated about, and then we also need to find some way to generalize the surface area of one of the cross sections. So what we're going to do next is we're going to look at one of these cross sections, because the bounds, I think, are pretty straightforward. In this case, the bounds that we have are from x equals 0 to x equals 3. And if that's not clear right now, I think we can kind of make it make a little more sense in just a moment. So let's focus on this idea of the formula for the area of a cross section. When we're working through these problems, I would highly encourage you to very specifically draw out this cross section. It makes it a little bit easier to trace if we go back to the original problem. So I'm going to go into this area that we had, And I'm going to draw a little cross section. So here's one of the, you can think about it as one of the rectangles maybe that gets rotated around the x-axis. And if we think about what would have happened to that rectangle when we rotated it around, let's say that just exists at some point x. Here's that same point x right here. We would have gotten a little solid that would have resulted in its rotation right here. So here's that being rotated around our little axis right there. So that's at that same point x. Now if we really focus on that particular shape, what we have is we have a circular disc. It's a solid little disc. Think of it as almost like a tuna can or something like that. And what we need to do now is we're going to focus on finding the volume of this disc. So how do we generalize the volume of this disk right there? Okay, so now since each of these cross sections that we would have drawn are perpendicular to the axis of rotation, so it really wouldn't matter where on this first drawing we had drawn this little rectangular cross section. It's perpendicular to the axis of rotation. So if we can kind of visualize rotating that around the x-axis every single time, we're going to get a series of circular disks. Therefore, it's easy for us to generalize the area of one of these cross sections because it's just a circle, and that leads us to the answer for number 2 here, which is the area of one of these cross sections is going to be pi r squared. Now the radius is going to vary depending where we are on the axis. We can kind of imagine, if we're drawing a disk very close to the origin, like maybe right here, that's going to have a very small radius. Whereas if we were to go further out, we're going to see that the radius of these disks gets larger and larger and larger. And that's because the distance between the axis of rotation and our boundary curve increases as we move further out there. So when we're asked to consider, to find a formula for the radius of the given disk, namely big R of x, luckily since these are all under one curve, we can say that this radius, which we're going to call big R of x, is simply going to be the distance from the axis of rotation to the boundary curve. The distance from the axis of rotation, the x-axis, to our boundary curve, x squared, in this case, is just going to be x squared. All right, so again, going back to that very first example of volume that we did last time, where we said we needed to find two things, formula for the area of a cross section and the bounds, we now have both of those. X equals 0 to x equals 3, and then x squared is going to be the radius, variable along this interval. So now we can go ahead and we can use this formula right here to then get our volume. So let's move into that. So volume is going to be equal to the integral from a to b of pi times our radius squared. It's just the area of a circle. That's all we're dealing with because we've got disks. And in this case, now that we've defined all of these different parameters, we can say that this volume is going to be the integral from 0 to 3 of pi times our radius, which is x squared dx. And at this point, we're ready to integrate. So hopefully we've got something that we can integrate now, and the resulting value will give us our volume. Now there's a couple things that that I might encourage you to do at this point. First of all, this pi right here, it's a constant multiple. I would encourage you to move it out, because otherwise it might end up being a little bit obnoxious in terms of the calculations that we're going to have to make later. So I'd clean this integral up a little bit. I'd pull the pi out, and we'll multiply it through later. So pi times the integral from 0 to 3. I would also, if possible, deal with this exponent right here. So we're going to go ahead and square x squared to get x to the power of 4, because we multiply those two numbers, dx. Now this is something that we can very easily integrate using our antiderivative rules, so let's go ahead and do that. So now that we've got this all set up, we can calculate our volume. So we will leave that pi out front. The antiderivative of x to the 4th is 1/5 x to the 5th, which we evaluate from 0 to 3. Again, constant multiples can just sort of be obnoxious, so I'm going to take that 1/5 and move it out as well. So we're going to have pi over 5, and then x to the 5th evaluated from 0 to 3. So we use the fundamental theorem of calculus, and we take that antiderivative and evaluate it at our upper bound, and then subtract the antiderivative evaluated at our lower bound. And I'll spare you some of the gory details, but this ends up being 243 pi divided by 5. And since this is volume, these are going to be cubic units, or units cubed. So this is an initial example of what we refer to as the disk method. And this is a nice little formula right there that we've got to kind of follow. Again, once we determine that the disk method is what we're going to use, we know that we need just two things. We need to determine these bounds, A and B, and we need to determine a formula for this radius. Again, that radius being the distance from the axis of rotation to the given boundary curve. All right, so that was kind of a nice basic example. Now maybe we'll move on to some slightly more complicated examples.